This is lesson 5.3, Hess's Law. Hess's Law says that if a reaction is carried out in a series of steps, the change in enthalpy for the overall reaction equals the sum of the enthalpy changes for the individual steps, no matter what order they're taken in. So, it does not depend on the number of steps or the pathway. This makes it easier to calculate energy changes that are difficult to measure, for example, ones that might release a ton of energy. Here's an example of Hess's Law. Calculate the delta H for the reaction carbon plus hydrogen goes to ethylene, given the following chemical equations and their respective enthalpy changes. So, they give you three chemical equations, and you need to reorder them in order to find the delta H. So the first thing you should do is look for one of the reactants. So we know we want carbon, and the only equation that has carbon in it is the second one. So we're going to write it out. And the delta H for that reaction is negative 393.5 kilojoules. However, we want two carbons, so we need to multiply this entire equation by 2. So here, I'm just writing the overall equation, what we're hoping to get at the bottom. So again, let's go back up here and multiply everything by 2, which means we have to multiply the enthalpy by 2 as well. So that gives us our 2 carbons, and now we want our hydrogen. So the only equation that has hydrogen in it is this third green one. And there's one hydrogen, so we can just leave this one alone. So hydrogen plus half an oxygen goes to H2O. And the delta H for this reaction is negative 285.8 kilojoules. Lastly, we want C2H2, but we need it on the right side of our equation. So we take the first reaction and we're actually going to flip it so that C2H2 is on the right side of the equation. And since we flipped it, our delta H must now be changed to positive 1299.6 kilojoules. So in the next step, we're going to cancel anything that's on the left side of the arrow that is also on the right side of the arrow. So we can see, by looking at our equation, for example, we have 2 CO2s on the left and 2 CO2s on the right. We also have 2.5 oxygens on the left and 2.5 oxygens on the right. And finally, we have 1 water on the left and 1 water on the right. So the only things that we have not canceled are the 2 carbons, the hydrogen, and the C2H2, which is what we wanted. So we know we've done this correctly, and now all we need to do is add together our delta H's to get an overall change in enthalpy for this reaction. So when we add these all together, we get an enthalpy change of 226.8 kilojoules. Another way that we can use Hess's Law is by using enthalpies of formation, which are written with delta H of F. So the enthalpy of formation is the enthalpy change when a compound is formed from its elements. And the elements have to be in their standard state, which is their pure form at atmospheric pressure and the temperature of interest, which is usually 298 kelvins. So the standard enthalpy of formation is the change in enthalpy for the reaction that forms 1 mole of a compound from its elements with all substances in their standard states. The units are always kilojoules per mole. Now, delta H of formation will always equal 0 for the most stable form of any element because it doesn't need to be formed. It's already made. For example, carbon as graphite, or hydrogen gas, or oxygen gas. There's no formation needed, so the delta H is always 0 because those elements exist in that state all the time. So here's an example of a chart that gives delta H of formation. You also have one in your data booklet. Now, the delta H of formation of diamond is going to be different than that of graphite because they are different compounds, or they are different substances. For example, for which of the following reactions at 25 degrees Celsius would the enthalpy change represent a standard enthalpy of formation? So if we look at the first one, remember we're forming 1 mole, so this one is good. And sodium is found as a solid, and oxygen is found as a solid, so this would be correct. It would be a standard enthalpy of formation. In the second one, we're forming 2 moles of KCl, so this would be incorrect. This would not be a standard enthalpy of formation. And in the last one, we have forming 6 moles of carbon, 6 hydrogen, and 3 oxygen, so these are actually the elements in their standard state, and this should be flipped to form sugar. So this one also is not a standard enthalpy of formation. So the only correct answer is answer A. We can use the standard enthalpies of formation to calculate the enthalpies of reaction. So this is another type of Hess's law problem, where the enthalpy change of a reaction can be found by taking the sum of the moles times the delta H of formation of the products minus the sum of the moles times the delta H of formation of the reactants. So here's an example. Calculate the standard enthalpy change for the combustion of 1 mole of benzene to CO2 and H2O. So here I've written down some standard enthalpies of formation for benzene, oxygen, carbon dioxide, and water. And let's write the equation for this reaction. So benzene plus oxygen goes to CO2 plus water. We need to balance it. And so we get 1, 15 over 2, 6, and 3. So, remember that delta H is equal to the sum of the moles of the delta H of the products minus the sum of the moles of the delta H of the reactants. So our products are going to be 6 moles of CO2, which has a delta H of negative 393.5, plus 3 moles of water, which has a delta H of negative 285.8, minus the sum of the benzene, so 1 mole of benzene times 49, plus 15 over 2 moles of oxygen, which is just 0. So we plug these into our calculator, and instead of doing a bunch of rearranging equations, like the previous Hess's law problems, we can easily get a solution to this problem just by the delta H's of formation. And so we get an answer of negative 323,267.4 kilojoules.